right, looks like we have a decent number of people still joining right now, but I'll get started with some introductions before I hand it over to Colin and Rich. So welcome everyone to today's webinar titled Don't Be Blindsided, Consequence Criteria for Facility Siting. I'm Stephanie, your host for today's session, and I'm thrilled to have you with us. Today, we'll be delving into a critical aspect of facility safety, the consequence criteria for facility siting. The consequence criteria used in a facility siting study determine whether a building is considered safe, but all too often they're chosen without complete understanding of the implications. Criteria need to be selected wisely, requiring a thorough understanding and consideration of the hazards, building vulnerability, and emergency response plans. No matter where you work or your involvement in these key decisions, we're here to shed light on the importance of informed decision-making in facility siting. Before we begin, I want to encourage you all to actively participate in today's session. We'll put up 2 polls during the presentation. We also value your questions, so please feel free to submit your questions throughout the webinar using the Zoho webinar Q&A box. We'll be addressing your questions during the Q&A session at the end of the presentation, but we'll also be recording this webinar and we'll make the recording available to you in the next couple of weeks. So now let me introduce our speakers who will be guiding us through today's topic. We have Colin Armstrong and Rich MacNguyen. Colin is the group lead and principal engineer of our quantitative risk group. He's served as the technical lead for numerous facility siting and QRA projects in oil, gas, LNG, and specialty chemical projects globally. He's experienced in all aspects of QRA, consequence modeling, frequency assessment, and scenario analysis. Rich is a senior engineer here at Accutech focused on process safety, risk management, consequence modeling, and quantitative risk assessments for offshore and onshore facilities. He's an analytical engineer with a focus on utilizing, developing, and implementing risk models to support clients with solving problems in process safety and reducing risk associated with hazardous facilities and operations. Both of them bring a wealth of knowledge and experience to the field of facility siting. They'll be sharing their expertise and insights with us today. So now I'll pass the virtual mic to Rich to kick off our webinar. Rich?
Thank you, Steph, for the introductions, and thank you everyone for attending today. So this webinar will focus on developing assessment criteria for the consequence-based facility siting study. First, we'll provide an overview of a consequence-based study in the context of facility siting and why it is important. We'll explain why developing proper assessment criteria is important for the facility siting study and how it influences risk management. We will address criteria specific to consequence types assessed in facility siting, which include fire, explosion, and toxic hazards. For fire, criteria considerations include the need to shelter in place or egress. If personnel need to shelter in place, the shelter-in-place building would require fire protection sufficient to withstand the fire hazards for the appropriate duration. The fire hazard type is also important, which in facility siting typically includes jet fire, pool fire, and flash fires. Fire criteria can be defined using thermal radiation or thermal dose. For explosion criteria, considerations include characterizing impacts specific to the vulnerable target assessed, which include buildings, people, and assets. Criteria can be defined using overpressure only or a combination of overpressure and impulse. For toxic, similar to fire, criteria considerations include the need to shelter in place or egress. Toxic impacts are specific to the material, so criteria can be defined using concentration endpoints, toxic dose, or Probit equations to estimate the probability of lethality. So what is a consequence-based facility siting study? These studies are typically the first step for facility siting. This type of study focuses on the impacts due to maximum credible events, or MCEs, that present the fire, explosion, and toxic hazards. Main elements of the study include identification of the hazard from the facility's processes and operations to buildings, people, and/or assets, development of the MCEs, quantification of consequence and impacts from the defined MCEs, and the study will develop recommendations for risk reduction options, which sometimes involve further study of buildings with severe impacts. So why perform a facility siting study? While the main objective is to understand the risk to occupied buildings, it answers the question, are people at my site safe? Reasons that may drive the need to perform a facility siting study typically include processes or operations that are known to be hazardous and have a potential to impact occupied buildings. Buildings are too close to the hazardous areas, buildings known or suspected to be under-designed to withstand potential impact from the hazardous process, siting new buildings, portable buildings, and tents to make sure they're optimally placed and meet design criteria for hazardous impacts, and determining optimal placement for new hazardous processes. So at this point, we'd like to take a poll. So the poll is about the populations that you could consider in a facility siting study. So please select all that apply to a study that you would typically perform. We'll give everybody a minute to cast their votes here. All right. It seems like we've got over 90% of the votes in. So looks like the front runner is on-site occupied buildings. So that makes sense. 92% of the votes identified this item as what they would consider in the facility siting study, which is expected because the facility siting study typically focuses on the on-site occupied buildings. However, it's interesting that also some people like to consider outdoor populations as well that are on site. So we've seen that as well for risk-based studies where on-site populations are considered for outdoor people as well. And then it looks like about 60% or so considered the neighboring industrial facilities and also neighboring communities. So interesting result. And we can then, let's continue then on to the rest of our presentation.
All right, thanks, Rich. Criteria used in siting studies are the ultimate decision point, which determines whether siting is adequate or needs to change. The impact criteria determines if building designs are acceptable relative to on-site hazards or new siting locations are safe. Proper criteria ensures that people at my site are safe, but the question becomes, when is the criteria proper? Well, that's when it ensures safety without being overly burdensome. Criteria must consider the hazard type, the emergency response plan, and the building construction. So for fire hazards, first we can divide these into two general categories. We have short duration and long duration fire hazards. The long duration fire hazards are pool fires, jet fires, and these present for an extended period. For buildings and building occupants, the primary hazard is impingement or very high thermal radiation levels. These can result in structure fire, temperature rise, or impairment of egress routes. A response concept must be chosen for long duration fire hazards if they can impact a building, and that response concept impacts the criteria that must be considered. The response concepts are generally to shelter in place or egress, and the response plan affects the hazards to people, and therefore the criteria that should be selected to determine if people at the site are safe. Short duration fire hazards like flash fires or fireballs occur rapidly. There is no time for response, and they either result in the immediate impacts or occur without impact. There's no time for response to mitigate the potential hazard. And so the driver of the impact and the criteria becomes the personnel's location and the building construction if the personnel are located indoors, or we're talking about an indoor offsite population. For long duration fire hazards, sheltering in place or egressing affects the hazard exposure to building occupants. Sheltering personnel are affected for the duration of a fire. They may be exposed to hazards from the building structure being ignited, if constructed of a combustible material, internal temperature rise due to the fire outside, and potentially smoke ingress as well. Defined shelters must consider how long personnel need to continue to remain in the building to operate the process, and how long it may be until the event is controlled. Shelters often require emergency response functions to be conducted after an event. So we need to consider the duration of the event and the duration that we need to remain and operate the process for emergency control. Once the event is controlled, people can then safely egress from the building, but they need to be able to shelter to withstand the duration of that design fire hazard. Where the response concept is to egress, we must consider that personnel may be exposed directly to thermal radiation as they attempt to reach a safe distance or a muster point. We may consider whether people will be shielded from thermal radiation during egress and how far people must travel. Are the exit routes located away from hazards? Does the building provide shielding from jet fires or pool fires? These all would affect the way that people are exposed as they egress from the building and can be considered in the criteria. In the case of fires that impinge or engulf a building constructed of combustible material, they may be ignited, and some personnel may be unable to escape when the secondary structure fire is ignited. Overall, we must consider the ability to shelter or egress to answer the question, are people at my site safe? Shelter-in-place locations must be designed to withstand engulfment, impingement, or high thermal radiation levels based on the maximum credible fire hazards identified in the siting study. Egressing personnel will be exposed to thermal radiation levels upon ignition of a flame, but may seek refuge. Probit analysis can consider the impacts to personnel by evaluating not only thermal radiation levels, but also the duration of the exposure. In the simplest form, these methods assume a person is standing still, exposed at the initial thermal radiation level for the duration of the fire hazard, or an assumed duration to reach a safe location. A dynamic egress analysis can be conducted to consider the exposure to a person who egresses away to a safe distance or a refuge location. In this case, it's considered how the thermal radiation level decreases during the exposure duration as personnel are moving away from the flame. The figure on the right is a plot from a dynamic egress analysis that evaluated the likelihood of a lethal exposure from fire hazards to personnel outdoors in a refinery. A defined egress plan was considered, and a Probit equation was used to integrate the thermal dose over the egress route, considering the egress speed, the thermal radiation profile of the flame from pool fires and jet fires, as well as the distance to reach safety. For asset damage, we must consider a number of factors when evaluating criteria for fire hazards. The materials of construction, safeguards, and escalation potential affect the acceptable fire impingement criteria for assets. Generally, assets are damaged by direct fire impingement, although high thermal radiation levels may damage some equipment like cable trays and instrumentation and electrical at lower levels. Criteria for asset damage can be found in the IOGP Risk Assessment Data Directory and other data resources. And a detailed fire hazard analysis can be completed to assess potential asset damage that could result from a loss of containment scenario resulting in a fire hazard. Safeguards designed to mitigate fire hazards may be considered when criteria are set as well. Although evaluation to ensure that the safeguard is effective to mitigate the hazard should be considered. For example, firewalls may not be rated for hydrocarbon fire protection, but rather structure fire, which presents lower thermal radiation and temperature profiles. A 60-minute A-rated firewall will not withstand a 60-minute jet fire. But for long-duration fire events, safeguards may include firewalls, fire rating, deluge, or other extinguishing measures, as well as effective detection and isolation measures that stop the flow of fuel to the flame and mitigate the duration of the fire event. For short-duration fires, such as flash fires, building occupants may be protected by buildings that are tightly sealed with positive pressure, interlocks to gas detection, and other measures. But if buildings have operable windows or doors that would allow for vapor ingress, or large bay doors that are maintained open, these factors should be considered in the siting criteria as well. Many times we see workshops and other buildings where work is done that have large bay doors. Always, when on site evaluating occupied buildings, I make sure to ask there, are these bay doors maintained open? Maybe we're there in the winter, they keep them closed to keep the building warm, but in the summer they keep them open at all times to allow for fresh air into the building and cooling. And in that case, we have a hazard of potential for flammable vapor ingress. Those people would not be protected in a flash fire event, where others may be. So I'll hand it back over to Rich, who's going to talk about blast criteria.
Thanks, Colin. So now we will provide an overview of blast hazards. So blast refers to an event that can generate overpressure, which can be generated from a variety of sources. The blast events typically assessed in the facility siting studies include vapor cloud explosion. So these occur when flammable vapor accumulates in an obstructed region, which has a certain level of congestion and confinement, and then encounters an ignition source. Upon ignition, the vapor undergoes rapid combustion, resulting in an explosion that can generate overpressure. Next is BLEVE, or the boiling liquid expanding vapor explosion. This can occur when a pressurized liquid vessel is exposed to external factors such as fire impingement, causing the vessel contents to reach a critical state. The fire and internal vessel pressure rise can cause the shell of the vessel to weaken and rupture, releasing its contents, resulting in a rapid phase transition that generates overpressure and a fireball. The image in this slide shows the fireball from a BLEVE. Finally, physical rupture of a vessel or pressure vessel burst can also generate overpressure. These can occur from runaway reaction, internal deflagration of flammable vapor or combustible dust, or decomposition. The blast wave, whatever the source may be, may result in damaging overpressure that can impact people, building, and assets. The blast hazards are characterized by overpressure and impulse, and both are important factors in determining the magnitude of impacts to vulnerable target, such as structures. The resulting impact depends on the type of target assessed, whether it be people, buildings, or assets, and the severity of the blast. To develop blast criteria, the characteristics of the target and their vulnerability to blast overpressure and impulse must be understood. For buildings, the blast impact is dependent on building construction. The literature provides building damage level curves for generic building categories that correlate damage with overpressure and impulse generated by the blast. The first approach is to use generic building categories, which is effective for assessing a large number of buildings. When many buildings are within a study, generic criteria can be used for screening analysis to categorize buildings into low and high impact categories. Criteria may be based on overpressure only or a combination of overpressure and impulse. Criteria based on overpressure only simplifies the analysis and is suitable for screening purposes, as the criteria will assume a conservative impulse. For a more refined analysis, criteria can be also consider impulse in addition to overpressure. Building-specific analysis can be undertaken when refinements are required regarding the building impacts. This is typically done to account for building-specific features such as blast resistance. With a detailed analysis, the blast impact can be refined to account for blast angle, and impacts can be determined more specifically to each side of the building and specific building components, such as windows and doors. Once building impact criteria are defined, it could then be associated with vulnerability for building occupants. For people outdoors, the criteria should consider where personnel could be located. Criteria are different for personnel located in relatively open areas compared to personnel within or near congested process areas, or large obstacles. As mentioned previously, blast criteria can be defined using only overpressure. When the criteria are defined by overpressure, the impulse is assumed to be of sufficient duration to cause damage and result in a particular occupant vulnerability value. This is a conservative assumption and may be overly conservative for short duration blasts involving small cloud volumes. The figure in this slide shows overpressure-based criteria for different building types and shows how vulnerability varies by building construction type. So, next slide, please, Colin. More detailed blast criteria can be developed by considering impulse in addition to overpressure. The pressure impulse curves, or PI curves, can be used to estimate the building damage levels. The PI curves may be based on generic building types or be specific to the building being assessed. Example PI curves are shown in this slide. Building damage levels are separated by curves on the plot, with building damage levels increasing as overpressure and impulse increase. To determine the building damage level, the overpressure and impulse from the blast scenario are plotted, and the region in which the overpressure impulse falls is the estimated building damage level. Once the building damage level is determined, the vulnerability of building occupants can be estimated, which is also dependent on the building type. Blast criteria can also be defined for asset damage. For asset damage, criteria are defined by overpressure, material of construction, and equipment type. The equipment type is important since the shape of the equipment dictates the magnitude of drag forces experienced by the equipment as the overpressure propagates. IOGP and other references provide guidance for criteria to assess asset damage due to blast overpressure. The table in this slide shows equipment and their estimated damage based on overpressure. Damage is specific to the equipment type, and varying levels of damage occur as overpressure increases. Damage ranges from broken windows and gauges at low overpressures to piping breaks and destruction of units at higher overpressures. Now I'll turn it back over to Colin to discuss the toxic criteria.
All right, thanks, Rich. So, toxics is the final hazard criteria we're going to cover here. And some of the most catastrophic incidents in the process industries have resulted from toxic releases. Toxic impacts can have a very large footprint depending on the quantity being handled, the conditions of the process, and the material toxicity. Toxic impacts are material specific, and the impact criteria and evaluation criteria needs to be specific to the material being handled. Assessing the impacts of toxic releases may be done by considering the concentration of exposure. Published values such as the AEGL, IDLH, or LC50 values can be used to qualify the hazards to personnel. Outdoor concentrations are predicted by dispersion models, and indoor concentrations can be calculated based on a building's air change rate to understand the potential exposure concentrations indoors. However, impacts based on concentration alone are generally very conservative. Published values and their effects are normally based on the onset of impacts to the most vulnerable population. Toxic dose and toxic probit calculations can be used to evaluate not only the concentration of exposure, but also the duration of an exposure. The impact of the exposure duration varies by material. For some materials, a short exposure duration is hazardous, while other materials require a longer exposure duration. A probit function accounts for this in the probit constants, which are material specific. The probit function correlates a toxic dose, which is a function of the concentration and the time of exposure, to a likelihood of lethality. And here you can see an example of a probit function for ammonia. And based on this probit function, we can see, for example, that a 10,000 ppm exposure may result in a 10% likelihood of lethality over a 2-minute exposure duration, but we can see a 50% likelihood of lethality for that 10,000 ppm exposure if there is a 20-minute exposure duration. As a comparison, ammonia has an IDLH value of 300 ppm and a 10-minute AEGL3 value of 2,700 ppm. And so we can see there how probit equations and the concentration values vary significantly. But again, those concentrations are defined to represent the onset of hazards and generally are defined for emergency response planning. The impacts from toxic hazards to personnel are dependent, similar to fires, on the response concept. Toxic exposures are long duration events, similar to long duration fire hazards. So the response concept plays a part in the criteria. If personnel are going to shelter in place or egress in the event of a toxic release. While sheltering in a building may provide protection from the initial cloud outdoors, vapor ingress can result in indoor exposures. And you can see on the right there some plots of indoor and outdoor concentration profiles considered in an air change model. Personnel can be exposed for longer periods if sheltering through a toxic release. And you can see that on the second plot on the right there, where the concentration indoors will remain elevated even after that cloud has subsided outdoors. Safeguards may be effective to protect people, whether sheltering or egressing. Respirators or SCBAs can be used to support safe egress or shelter in place. And toxic refuges may be tightly sealed and equipped with toxic gas detection, HVAC shutdown. Scrubbers or elevated air intakes or breathing air supplies may also be considered to protect occupants and allow for safe refuge. The protection measures that are considered should be considered in the criteria. Understanding the building's air change rate is critical to understanding whether shelter in place can be done safely. Assuming buildings are tightly sealed is not generally acceptable and may be incorrect. For an example, we worked with a client a few years ago, and their control room, as they thought, was very tightly sealed and they'd be able to shelter in place through a toxic release event. They had an event occur and ended up having to evacuate the control room before emergency response could bring the release under control. And that release went on for a very long extended period of time. There was no one in the control room who could monitor the process at the time. And it turned out that that building actually had a very high air change rate. It was not well sealed. And that's what resulted in significant toxic concentrations indoors that necessitated evacuation. All right. So we're going to go through another poll here, which I think Steph should put up on the screen. But the question here is, how have you used facility siting to inform your site emergency response plans and risk reduction? We know that generally siting is done to evaluate occupied buildings. We may evaluate off-site populations and on-site populations as well. But it has many uses to inform emergency response plans and other risk reduction measures. And so the question is, how or have those of you here used it to do things other than, say, just designing and retrofitting occupied buildings or locating occupied buildings? See some results coming in here, but it's a multiple selection option, so I'm sure it takes a moment to go through the list. Appreciate the poll responses here. I'll publish it, even though there's still some results flowing in, but obviously we see most likely, most voted answer here to locate the occupied buildings. That is the classic reason facility siting is done. Although we do see A good number of people using it as well to develop emergency response plans. A few less using it to evaluate egress routes or muster points. It's very much something we need to consider, especially if our plan is to egress. Are people going to be able to safely egress? Is that an effective response plan? And we see even lower there determining PPE requirements. So, okay. I'll take those poll results down and pass the torch over to Rich here.
Thanks, Colin. So now we'd like to just provide a quick overview about what could happen if the criteria are defined improperly. So there are a couple of different cases where criteria can be defined improperly. The first can be that the criteria could be too conservative. This can lead to an overestimation of hazards and result in too many high hazard scenarios. The result is that it may be difficult or impractical to meet criteria. For example, if a study defined the vulnerability to toxic hazards based on the assumption of a 30-minute continuous exposure to toxic concentrations, then the analysis would likely overstate the toxic hazards to people who could evacuate crosswind and have a lower exposure time. This would overestimate the toxic exposure and may cause the analysis to recommend safeguards that are excessive and not proportional to the level of exposure. The criteria can be, on the other hand, too optimistic or too lenient. This can lead to an underestimation of hazards and even a failure to identify hazards. When hazards remain unidentified, people could unknowingly be exposed to hazard. An example of this is an assumption that personnel could egress through toxic and thermal radiation hazards. If a study makes this assumption, then toxic and thermal exposure hazards during egress would not be identified, and risk reduction measures such as the need for self-contained breathing apparatuses or thermal shielding may not be implemented when required. Lastly, criteria may just in general be not appropriate for the hazard being assessed. This results in a failure to properly address the hazard, and the study may over or underpredict the hazards. Generally, these hazards would be miscategorized or mischaracterized. So overall, the level of analysis can be grouped into three overarching categories: a simple / screening, advanced or detailed analysis. The siting study should define criteria at a level appropriate to the detail required to properly manage the hazard. For screening purposes, simpler but more conservative criteria can be used, such as thermal radiation for fires, concentration endpoints for flammable and toxic gas dispersion, and overpressure for blast. As a subsequent refinement step, the study can focus on vulnerable buildings where impact results in increased risk to personnel. At this point, more advanced criteria can be used that factors in the time element, such as thermal dose, toxic probits, and PI curves. If a further analysis is required to support safe building design and proper risk management, a detailed approach can be pursued, which involves specific analysis of high-risk hazards. For example, if a building is particularly vulnerable to blast overpressure, then a detailed structural analysis can help identify weak points to reinforce, which would then increase the building's blast resistance. Sorry, Colin, you're on mute.
So overall, proper criteria needs to consider a number of factors. For fire, we need to consider the difference in fire type, whether they be long or short duration fire events. We need to consider the building construction. We need to consider the duration of the fire event and whether people will be outdoors egressing from the flame or indoors sheltering in place. For blast, we need to consider the building design, the pressure and impulse, the existing mitigation measures, and impacts to both personnel indoors and outdoors. Again, as Rich mentioned, there's different levels of detail we can get to in that blast analysis. And for toxics, we need to consider the unique toxic chemical properties, indoor and outdoor concentrations based on the air change rate of the building. We may need to consider the HVAC system design and how that affects the ingress of air into the building, as well as maybe other existing safeguards that might be present, things like PPE, respirators, SCBAs, breathing air supplies. But the overall takeaway is that criteria is not universal. It's not universal across facilities, hazards, or buildings. It must fit the analysis, as we saw on the last slide. There's different levels of detail we can get to, and we can't always be working at the highest level of detail due to time constraints, but it needs to fit the analysis and also the site-specific scenarios. So we appreciate your time going through everything here. I'm going to open it up. We're going to switch over and take a look at some questions that came in.
Yeah, so we've got a few questions that came in. We've got a few minutes to answer some. So let's start with this one here. Can you explain further why positive pressure within the building should be considered for flash fire?
Yeah, so positive pressure is really an indication that a building is tightly sealed against air ingress. It means that the fresh air intake to the building is sufficient to ensure that we don't have air ingressing into the building through leak points. At the time then that an HVAC system would be shut down, that positive pressure would start to decay, but it limits, once that HVAC system is shut down, it limits the ability of air to ingress into the building. If that positive pressure is integrated in with an elevated air intake or some other fresh air supply, depending on the hazard that's been identified, it may be able to entirely prevent, say, a low-lying gas cloud from ingressing into the building.
Right, and let's see here. We've got, are you modeling dust explosions? If so, how?
Yeah, so dust explosions are something we run into often. We do have a group that specializes here in dust hazards and does dust hazard analyses. We often support them in that analysis. And generally with dust explosions, we're evaluating the potential pressure rise in confined dust environments using applicable fire codes to determine the source overpressure for dust hazard events.
Let's see. So there's a limited number of published probits. What do you do when one's not available?
So I could take that one too, I guess, but often, even when there is not a probit equation readily available, we can find test data that's been done to evaluate the lethality of toxic hazards, and that's quite common that we run into that issue. And there are published methods to correlate that test data, which usually comes from animal test data, to evaluate and determine the lethality and probit values for humans. So you can find methods on that, for example, published in the T&O Green book.
We've got a question on natural hazards. Do you consider natural hazards, hurricanes, tornadoes, flooding part of facility siting, or are these addressed by building codes only?
Yeah, so I can answer this one. So we typically would not include these natural hazards in facility siting, like you're mentioning in your question. These are typically designed specific to the location, and the building codes would address these type of hazards. With facility siting, we're really looking at the hazard from the process and how it may impact building occupants. So natural hazards would be something considered more in like a hazard identification type of risk assessment, which would be more of a qualitative assessment about those hazards.
So we've got maybe time for another couple. Here's a pretty broad. How can QRA help in deciding facility siting?
So I can answer that one as well. So that is actually our next webinar, where we talk about risk-based facility siting study, which is very similar to QRA. Basically, this one is focused on consequence-based, which is half of the equation for risk, when we incorporate the likelihood at which some of these hazards may occur, then we're able to understand the risk. So, a risk-based facility siting, like I said, is very similar to QRA, and it can help then hone in on the hazards that are presenting a higher risk. Whereas in a consequence-based study, you're really looking at some of the maximum impacts that could occur. So in that way, I guess to directly answer the question, QRA can help in a facility siting study by incorporating the likelihood element into it. And then once you understand the risk level, you can identify the appropriate risk mitigation measures appropriate to the level of risk.
One last question. Have you published an article on this topic? Do you have a white paper?
Not on this specific topic, but the recording of this presentation will be available. We do have a number of papers we've published on facility siting topics, but I can't say we've done one specifically on consequence criteria.
Great. So thank you. That was a wealth of insights into the world of facility siting. I want to extend our gratitude to our speakers, Colin, Rich, for sharing their expertise and shedding light on the critical importance of consequence criteria in facility siting. I also want to express our thanks to all of you for joining us today. Your active participation in the polls, the questions made this webinar engaging. So as Rich said, this is part one of a two-part series on the topic. So stay tuned for an announcement on part 2 early next year. And for those of you who submitted questions that we couldn't address at the end of this session, don't worry. Our team will follow up with you individually to provide answers. Your curiosity is what makes these discussions really valuable. So we'll also be sending out a link to the recorded webinar once it's available. Feel free to revisit the content, share it with your colleagues, or delve deeper into the insights provided today. So once again, a big thank you to our speakers, and thanks to all of you for being part of the discussion. And we look forward to connecting with you again in future webinars. Thank you.
Thank you.
Thank you again, everybody. We'll see you next time.